Hello, everyone. My name is Tomas Hruby, and I work as an engineer at Tigera, and I'm responsible for the eBPF. I'm here to talk about the eBPF data plane. I think that was already a question asked before, but how many of you are using or considering using eBPF? Considering. What's your reason for considering it? Is it because it's performance, because it's hype? Whose performance? All right. Yeah. So this way. So I got here some quotes for our current users, and this is their reasons to use eBPF data plane instead of IP tables. So performance and resource utilization is the prime thing. And as Reza was talking here in the morning about data planes, Calico is primarily a control plane for a data plane, right? So you specify your policies and you specify what should happen in the cluster, and that's written into some control plane, and the control plane is doing the heavy lifting and is actually passing the packets. Right? Normally that's done by Linux kernel, net filter, IP tables. So when you install Calico IP tables, you're pretty much installing just the control plane because the data plane is already there. With Calico eBPF, we also distribute the data plane. How many of you are familiar with what eBPF is or use the technology? Right, so I'll give some brief introduction. You probably heard it many times somewhere else, but eBPF is a technology that allows us to inject code into the Linux kernel. And this way we can modify what the standard Linux kernel is doing. And what's the coolest thing about that is this is the first time in Linux history we can do it in a safe and secure manner. Right? The first kernel I think I installed was like 2.2 or 2.4, and that was difficult to find a driver for anything, and if you loaded a driver, it probably crashed sooner or later somewhere, right? So if we ask you to install a module into the kernel and promised you that things would be better, how many of you would do that, right? Would you trust us? It's kind of like sending you an email with like, click on that link, right? So with eBPF, we pretty much got to the point where it's safe to click on that link because you're going to execute code that the kernel is first going to verify whether it is safe to execute, whether it's not going to crash the system. That doesn't say that your system is going to work correctly. Be aware of that. So if you load a program that is just going to drop all your packets, well, it's dropping all your packets, but you can still use, say, serial console or something to get rid of that or reboot, right? And the code that we inject is just acting upon events. Essentially, that's the whole kernel acts on events. And so the code is executed at certain points when the kernel comes across the points where the code is injected. So you can these days inject the eBPF code in so many places, I can't even list them all. And we use one place specifically, and that is the TC layer, and I'll get a little bit later into what that is. So with that, what eBPF allows us is to take a stock kernel, which is pretty good in doing kind of everything, but something that like fits all is never perfect in a specific task, right? And what in eBPF, what in Kubernetes we do, the host is essentially working as a router, right? You get a packet on one interface, it looks where it should go to another interface, your pod interface, and it needs to get a packet there, and it may do some address translation because it implements services. So with eBPF, we can optimize for that use case. IP tables, networks, net filter, it is really good in doing that, but not perfect, because it has to cover all the corner cases and all the other use cases. So if you look at how a node looks like, you essentially have a node with some external interface, and you have your pods with other interfaces. So somewhere in between sits the network stack and primarily the IP tables where the routing happens, the network address translation, security, all that stuff, all the filtering, right? So when normally a packet enters, it goes through all that. With eBPF, we can, at the entry of the interface, look at the packet. At the time, we already know what to do with the packet, and we can pass it straight to where it needs to go, right? So it doesn't mean that we don't do what the IP tables would normally do, but we do it essentially in a single spot, right? Here we would have to go through multiple hooks, routing would be involved somewhere, so on. The packet would kind of execute through multiple stages. We take the packet and we pass it where we need to. And this is where the eBPF data planes, and ours is not the only one, gain most of the benefit on bitrate. I think maybe I didn't say it quite correctly, but one of the reasons why IP tables is also problematic, and if we go back to the first quote where the user said, programming the data plane takes time. The problem is that IP tables have multiple users. If you use Kubernetes, there's kubeproxy as a heavy user of IP tables because it has to write all the services into the IP tables. At the same time, Calico is trying to write the policies into the IP tables, right? And not to trample across each other's work, you have to take log, it takes time. Essentially, you do IP table save, IP table restore all the time. You have to make sure that if you wrote something, someone didn't remove it like 5 minutes later, and so on. There are also some third-party users, and it's becoming a little messy. So, actually, the newest version, I swapped the slide, so I'll come back to that one. Another reason why IP tables is a bit of a problem is that if you have lots of services, and in some of our examples, you may have really a couple thousand services, the rules are sequential. So if kubeproxy writes like 1,000 services, there's essentially 1,000 rules which are executed one by one. So if you happen to have a service at the top, it's resolved pretty quickly. Even though that is an overhead that is once per connection, if you have too many short-lived connections, it adds up, right? And if you have a service that is kind of at the end of the list, and that's a service that you hit often, and you have absolutely no control about whether that's going to be the first one or the last one, then the overhead is big. So in eBPF data plane, we solved those problems by first removing kubeproxy. That's a necessity because since we bypass the IP tables, or we want to bypass the IP tables, the kubeproxy rules won't be executed, right? So kubeproxy is now provided by Calico, and Calico doesn't write into IP tables. So the problem with contention on IP tables is gone. The kubeproxy rules are in a separate table, or in eBPF, all the permanent persistent data structures are called tables, even though they may not quite look like a table, or actually a map. So the kubeproxy rules are written in a separate map, and the other stuff that Calico uses is written in other maps. So those things can be written completely in parallel, as no contention. Obviously, one of the problems is the third-party rules, which you bypass almost in all times, except when those rules are in input and output channel. Those can't really be bypassed. So I think Mirantis distribution uses those third-party rules a lot, and we do cooperate with that pretty easily. And the other thing is that when we write the kubeproxy rules, they are not sequential anymore. They, in a map which is a hash map, or something that resembles a hash map, so the lookup is pretty much constant for all the services, so it doesn't really matter whether you have one service or whether you have 10,000 services. So this is a diagram how it works inside the Linux kernel. These boxes are pretty much the IP tables, and this is where the BPF can be hooked in. So when a packet comes in, hits the BPF program, jumps over to the device where we need to go. Previously, kubeproxy was implemented in somewhere where the IP tables mangle and do DNAT, and the policies were implemented where IP tables filter. Now, that's all distributed across the devices. I also mentioned here XDP. XDP is, yeah, that's more or less optimization. We use it. We also use it in IP tables mode, to be honest, where we have no track policies. So that's the first place where you can hit the packet, and if you have a DOS attack or something like that, then you don't have to spend many more cycles. But let's ignore the XDP pass because that's really just an optimization. And we hook the BPF at the TC layer. And if you zoom in, you have device. Right below that is TC, which stands for traffic control, and QDisc, which is queuing discipline. That's a technology in Linux since ever, which is used for traffic shaping and filtering. So that's where they decided to put the hooks for the BPF programs. We have two programs attached to each device. One is for handling ingress, and the other one is for handling egress. As the project evolves, it's actually a whole chain of programs for reasons that I'm going to talk in my next back-to-back talk in more detail, if you are interested. And as the project evolved, what we realized that loading all those programs and like big programs has an overhead. The verifier takes quite a bit of time to actually verify that the programs you're loading are correct. So if you were to spin up yet another pod, you would have to do the verification again, but we pretty much verified it already. So what we've created is more or less a library of generic programs, kind of like a share library. Like in the Kubernetes world, nobody really cares about share libraries anymore. But for the performance here, it pays off because we load those programs at the startup. Those programs don't change, and we only load like a really tiny programs at each device. And that is fast, and they just configure the rest. Another thing is where the policy is actually executed, right? Because you have, each endpoint has a different policy. So if you have a bunch of generic programs, where do we load the policy? So there's a library of policy programs per device for each direction. And the generic program just jumps into that program and gets back into the flow if the packet was accepted. If the packet is dropped, then it's dropped. There was a question about how to debug policies. With the eBPF data plan, you can dump the content of each of these boxes in a human-readable form, so you can kind of read what each of the boxes is implementing, whether that matches what you would expect, and you can go as low as dumping the real assembly, which is probably not where you want to go. Yeah. And I think in 3.26, we've introduced yet another program. Imagine that you have a production cluster and it's not doing what what you expect, right? So you want to get some login. And previously, we would turn on login, that would be a waterfall. That's super slow. It would impact performance of your in-production workloads. So essentially, you can't debug in production. What we have now is we can load a filter program that uses the same expression as TCP dump. As a matter of fact, BPF, the original BPF, was invented for TCP dump, right? So the PCAP library can spit out BPF code, which we then translate into eBPF. We load it, and you can say, all right, I just want to see the SYN packets of those particular connections and not log everything. So hopefully that will help the community to provide us with better repros of issues or with more insight from their production environments when they have problems. So that's, I think, was introduced in 3.26. Don't get scared here. This is the workflow of inside the eBPF programs, but there are two common paths. The first one is essentially we get a packet, we do contract lookup in our own contract table. We don't use the Linux contract table. If the connection already exists, it means that it's been approved before. We jump all over to the accepted part, we route the packet where it should go, and it goes. Right? That's 99% of packets. If we may have a miss in the CT lookup, we treat it as a new flow. We have to go through the policy. If it is accepted, we create the contract entry and route the packet. Every other packet on the same flow is going to take the short path. Right? All the rest is handling corner cases, and I will talk about it later why eBPF is not that straightforward. So I've been talking about kind of the details of how we implement the policy. And let's take a step back and what eBPF actually allows us to do differently except performance. Right. Imagine node ports. So if you have a node port, then any packet that comes to your node, if it is local, it just gets delivered to the local pod. If it is not, what happens is it gets forwarded, right? Unless you have the external cluster policy local, in which case it would get dropped. But what happens if it gets forwarded is that because the return traffic wouldn't return to the same node, it has to get masqueraded. So it comes here with this node's source IP. What's the problem here for you as a user?
It's very difficult to find which application access to the my service. No?
Policy, right? You don't know who's talking to you. You think that anyone on that node is talking to you, while you want to know that it is that client somewhere outside who's actually allowed to talk to you. So it makes it difficult to write policies. Right. All the load balancers are kind of node ports, and you can have clever load balancer that kind of sends it straight to the node where it lives. That's perfect. But if you really don't want to spend that much time on configuration, you can use this option where the packet comes in. You see, oh, it has to be forwarded. So we pack it into a tunnel. We preserve the packet 1.1. Gets to the destination node, we unpack it with the client source, and we can write the policy as you would like to. If you care about the performance a lot, and with the external traffic policy, you essentially avoid that extra hop. But if you still want to use this, we've introduced what's called direct server return mode. So you save the hop, goes back, but you can go straight back to the client. That, for instance, works in Azure pretty well. It depends whether your environment allows that. Another Interesting aspect of eBPF is what we call connect time load balancer. Right? In what I've been talking about so far, and in IP tables, you essentially get a packet, you look up what the translation should be, you rewrite a packet. That makes connection tracking complex. You have to modify the packet, you have to recalculate the checksums, whatnot. That's not negligible per packet overhead. But what if we can hook into the connect call, right? You essentially say, you want to connect to this service, hold on. No, there's this backend pod, and let's go straight to that backend pod, right? So with that, you have no per packet overhead. That's a great win. And that's the good thing about connect time load balancer. Oh, no, that's the bad, bad part is, for instance, UDP may get stuck. Imagine that you have a UDP application that asks your DNS server, it connects to the service, right? You can make a connect call on UDP, so all the packets are being sent to that one particular backend. And then the backend dies. And it keeps sending it there, right? So that's a problem. Another problem is service mesh. How many of you use some sort of service mesh? Okay, so that's a problem for the two of you. But hopefully we have a solution here as well. But luckily it's not a problem for the whole room. So that's the ugly part of solving the problem. The host network processes, they essentially need CTLB. And host network processes are not just the processes that kind of run outside of Kubernetes. You can have host network pod. Like Calico nodes essentially run as a host network pod. The problem it is because there is no way for us to kind of hook these packets before it gets routing all that. What if there was a default route, that would be great. We would hook it at some device, but what if there is not, or what if it goes to a device which we don't handle? So what we've introduced in, I think also in 326, is a web pair that allow us to hook those packets. And what happens is if you turn off CTLB for the host processes, and the process goes to the routing, we say, hey, by the way, it's a service, go to the device, we intercept the packets here, send it back, and then the routing either sends it out or to the pod. Since the inception, we were able to disable load balancing. At the time, we didn't see the problem, so we have a load balancing enable on and off option, which we're deprecating now. And we replaced it with load balancing you can choose for enable, disable, or enable it just for TCP, because that way we avoid the problem with UDP. And then whether we enable or disable the ugly part. Since 327, the default is that CTLB is enabled for TCP. TCP can resolve all of that backend pods on its own. And is disabled for UDP by default. With the service mesh, the sidecars, they essentially need to see the packets with the service IP on the wire, inside the pod, inside the IP tables. And with the connect time load balancer, they would see the backend pod, so they would not intercept that traffic. So if you want to use sidecar, and if you want to use Linkerd or any kind of mesh, you essentially need to disable load balancing fully, enable this other option, and it's kind of like a carpet bombing. So what we are considering is that we would just allow some sort of annotations to say enable, disable that per service. That's the nice benefit of actually being the provider of kube-proxy, that we can actually make these changes. So Another problem we recently came across with eBPF data plane as a discrepancy as a deviation from IP tables is that no local DNS cache assumes that you essentially run in IP tables mode and then you have kproxy. That's the bad part of being the provider of kproxy. When no local DNS cache starts, it injects some IP table rules to snatch the traffic before it gets translated. But in eBPF mode, by the time the packet gets to these rules, it is already translated. So it's kind of like eBPF is organized different than IP tables. So in 327, we've introduced an option to exclude certain CIDRs from the translation. In 328, which is coming very soon, you can actually annotate a specific service. So if you have DNS, you just annotate the DNS service, and then you install no local DNS cache, and it should work. So to conclude this part of the work, eBPF brings better performance, but and it leaves more room for security. I think that many people are not just interested in the pure bitrate. I don't know how many of you have single connections on like 20 plus gigabits per second. I don't know. But what it leaves is that even though you may not need that bitrate, you have lower CPU usage. So that security that you install into your cluster comes with smaller price, right? So you don't need to have such a beefy machine. You have more cycles to do your actual work, and it's easier for you to argue that security should be installed. It allows us to deviate from the default Kubernetes behavior for good and bad. So we can introduce options that otherwise we would have difficulty to bring it into mainstream Kubernetes, and you would need to install different Kubernetes, but some users just want a slightly different behavior. The downside is that if the mainline Kubernetes come with a different feature, we need to catch up with that, because then the users come like, hey, you don't support this yet. The main feature in the upcoming release is that we're going to support IPv6 dual stack. In 327, we released an IPv6 only preview, but that works only if you have like a pure IPv6 environment, which unfortunately is typically not the case for public cloud. So with that, you should be able to have a mix of IPs and IP versions. And even though we maybe not like releasing like these sexy features very often, as the project matures and Calico is pretty old, and even this data plane is almost 5 years old, then it's good to keep an eye on the project, because we are improving the performance and we also improving the conformance. There are many ways how we can still improve performance, like we can implement the tunnels and overlays in eBPF. We can try to reduce some routing, some hops. And with the conformance, we obviously are looking into an option to disable CTLB just for pods, so it would improve cooperation with mesh. And with that, I would like to say that it's a very lively project, and it's rapidly evolving, and you should keep your clusters updated, because we try to backport fixes and features into previous releases, but sometimes just as the code evolves, it prohibits us from going like too far back. So I'll take a break here before the next presentation, and if you have questions, there is a mic in the back, and shoot questions.
Yes,
You are first.
I have two questions. When will you adopt the eBPF data plane? Because it looks something new for me. And the second question, you told about some functionality like TCP dump for eBPF. Does it impact performance? And it is how?
Right. So the first question is, if I get it correctly, if I'm new to eBPF, how is it different to me?
No. How long? When you adopt the eBPF data plane in Calico? Because it's something new for me.
Like when you should adopt it?
So when did we introduce the...
Oh, when did we introduce that?
Yeah.
Oh, we introduced that 4 years ago. I think the
2019.
yeah 2000 I think just before the pandemic hit. I think so. It's we have seen posts on LinkedIn like Calico eBPF is not ready for production. You have seen the quotes at the top at the very beginning. It is used in production. I think those 6,000 node clusters using Calico 321. We are at 328 now. So it's getting to pretty robust data plane. And the second question was the overhead of TCP dump?
Can I use it on production server, on production cluster? Does it impact the performance?
If you do TCP dump or that login?
TCP-like...
Obviously, it impacts performance because you store login. But with those filters, we are trying to reduce the impact to bare minimum. So you don't have to log every single packet. You just log that one connection that you debug in.
I have multiple questions. So first of all, so what's going to happen for the packet journey in the ingress? So we talked about the services, but not the ingress.
Yeah, well, you can have services anywhere, essentially. So I think what do you mean by ingress is ingress into your host?
No. I mean, when you have an ingress rule, you have a TCP ingress rule. So it's going to come to the Nginx or whatever. And then it's going to another service, and then it goes to the pod. So if we have eBPF, how it is going to be changed?
I may not fully understand.
He's talking about the type of ingress, like an ingress controller, right?
Yeah, I mean,
Right.
ingress controller.
Yeah. I'm not sure I'm technical enough for that, for how that works.
So, okay.
I believe
you got me.
It's on the higher level, right?
Yeah.
When packet arrive to the cluster, then it goes through the ingress and then it goes to the service.
Is it like a load balancer? And yeah. Well, that's outside of us, right?
Yeah, but ingress inside the load balancer.
Yeah. Well, we don't break connections. Like it would get all the way to that ingress controller, whatever the ingress controller does with that. But I'll see you after the talk, and let's discuss that. And
also, it depends when ingress controller, if you're exposing to node code, you just reach node, and after that, you do get handle. So how you're exposing your ingress as well.
yeah, sorry, I don't know how that works.
There is a question.
What differentiates CDM
From us?
Yeah.
Well, internally they have different architecture. We do things our way, they do things their way. I think what primarily differentiates Cilium and Calico is that we use multiple data planes. So if you don't have a use case for eBPF, you can just happily use iptables with everything working is rock solid, which is hard to say about any eBPF data plane at the moment. And you work with legacy tools and all that. We can also have, as you said, Windows. We can have mixed cluster with iptables and Windows. which you can't have with Cilium. But otherwise, both data planes are pretty much providing very similar stuff. We have a document, we have a post now online which summarizes the differences. They have some features which differ, like Cilium policies are different than Calico policies, but both sets of policies implement Kubernetes policies. So, really.
The main proposal is Cilium brings the argument that it brings observability. So in terms of observability, how Calico with eBPF.
Right. I think that comes more or less to like a business decision. With Calico Cloud or Calico Enterprise, you have pretty much the same visibility, maybe even better. I don't know. I never compare that. But they open source and they provide that in right away. We don't do that. You can take some. I think Reza knows more about that. Some third-party tools that would provide you with some logs and that stuff. So yeah, that's more or less a business decision.
Thank you.
Should we go to the next session?
I just got one question. So, I'm not sure if you mentioned or anyone else mentioned already before. So, what's the use case for using VPP or using eBPF? Like, where would you? What reasons would you have for choosing one or the other?
Yeah, great question. That comes back to the difference between Calico and Cilium, for instance, that you can pick the data plane which is the best for your use case. So VPP is these days used a lot in Gen AI workloads, and security is super important in those workloads. So if you happen to run such a workload in such an environment and you run VPP, then you can run Calico and secure such a cluster with Calico, which you can't do with Cilium, for instance. So whether you want to use eBPF or iptables, it usually comes down to your own evaluation, whether it is worth to go with something, if you're conservative and you don't want to go with something new, but you don't need that high performance, iptables is just fine. But if you get to a certain scale, iptables is just not fine anymore. So really, evaluate it, try it out, make some educated decision.
You want to tell like the VPP data plane was GA, the Calico VPP one?
Yeah, VPP was GA'd in 327, right?
Yeah.
Yeah, and it is we don't support VPP as a company, as Tigera. It's being contributed by Cisco, and they maintain it. They maintain VPP, and they maintain the plugin for Calico. And another anecdotal thing for Calico is that we actually know that other companies are using Calico as a front end for their own in-house backends. I think that one big provider in Asia is doing that, and I know for sure that one company in Ottawa is providing a backend where Calico actually runs in hardware, and they use Calico as a front end. So from a user perspective, it's the same thing, just the data plane is different and tuned for the use case. Yeah, I think. All right.
Is this like if we switch this to this eBPF, is it like we have to switch all the nodes, or can be applied to?
Right. You had a question, and I wanted to touch on that. Hold on. This is going to explain that. For instance, that's a problem when you have a mixed environment. We don't support it actively. Obviously, we would like to support it. It comes down to cycles and needs from user base. So I would say 99% of cases, it just works. but there are the corner cases which may not work. So here in this case, if we send the encap packet to the other side wouldn't know what to do with that.
If I recall correctly, that was a
That's a node
case
port.
of optimization where you skip the
Right. Right, it's an optimization, but that's the only way how we currently implement node ports. Obviously, we could go with like backward compatible node ports. We
so
don't.
there's no option to turn it off.
Not at the moment, but if we hear from the community that that's what the community would like to have, we will do it. Or if the community contributes that would be the best.
There's one more.
Assuming we don't run node codes at all, can we use it combined with some nodes use eBPF and some nodes no?
Yeah, I think that would fall into this 90% use case where there is nothing like that this node really needs to know how the same thing is implemented on that node. This node will try to connect to a service. If we just put the backend IP in the packet, the other node would see a packet. This guy, if the service is resolved by Q-proxy, that guy doesn't really need to know about that.
It's a use case we need because we have thousands of nodes and not all of them are kernel 5. So we are upgrading slowly when we install nodes. So we want the ones that we put kernel 5 on them, we want them to use eBPF, right? And the other ones no.
Right. Used for by Red Hat kernel. Oh, okay. Yeah, that's the other thing with CentOS. That some of that should work, right? CentOS 4 kernels have lots of eBPF.
Yeah, it's kind of, the kernel version is quite interesting on Red Hat and CentOS.
Yeah.
They have a team that backports 90% of the BPF work, so telling whether your kernel supports BPF on Red Hat is quite difficult because it may well do even though it looks like it shouldn't from the version number. But yeah, Red Hat backports is...
Yeah, it might be actually good to test it out on one of your kernels and you might actually be good to go, but...
You tend to find out pretty quickly because the kernel will reject the BPF programs and Calico will commit an error if we're trying to use a feature that isn't there.
Yeah.
Because the verifier verifies all the features that you put in the BPF program. So if you try to use a feature that doesn't exist on your kernel, it will
We should go to the next session, Tomas.
Yeah, that's...
Can I use
I
two
think we'll be good with
deployments of
that.
Calico?
Oh, sorry?
Can't I use two deployments of Calico on one cluster, but one of them is implementing eBPF and one of them is...
I don't know. I wouldn't go that way. There's so many scenarios that we would need to try and support that we just can't cover that. So what we tend to do, if you have a specific scenario and it doesn't work for you, give us a GitHub issue, see us on Slack, and we can work it out with you. But essentially, it's only as much as we can do. Yeah, and even with like I'm kind of overflowing into my next presentation, but this is related to that presentation. Is even with eBPF, like what is supported on 5.4 kernel, which is the oldest we support, and what is available on 6.5 or whatever is the newest, like I think 6.7, that's vastly different. So we essentially support some subset, Cori technology, which is compile once, run everywhere, kind of allows us to use optimize for the newer kernels at the load time, but yeah, it's not standardized. I'm going to talk about BPF helpers, which is the way for the eBPF to interface with the kernel. And I think the kernel community essentially dropped the idea of BPF helpers because they were kind of like a standard API to the kernel. And now what they do is they have kfun. And that exposes almost like an arbitrary functions in the kernel, and they treat it as non-stable API. So even though we may use some of the features, kernel changes, the prototype function changes. Do we support it or not? Yeah. That also allows us to deliver some new features in performance, because now we can, with the kfunctions, interface with Linux contract, for instance. One of the issues is that we run in iptables mode, and then you upgrade to eBPF mode, and what happens to the connections that lived before that, right? And now we can actually grab that entry from contract, which wasn't possible those 5 years ago. So
let's
yeah.
go into the next section.